All right, so this is the conservation of mechanical energy lab. And this lab naturally follows the labs that we had done in the past with forces. Now, is that glare in the top a little bit too much, or can you see that okay? You seeing that okay?
It's not blocking too much.
Okay, yeah, it's going to go away in a second. It's just a way to, for some reason, the sun's in a weird configuration. So anyway, I won't write too much on the whiteboard tonight anyway. This is a fairly short lab, and so the coming into this lab, we're talking about the concept of energy, and honestly, coming out of Newton's laws, we have this great confidence that we could take a system at time t1, and we know exactly how we can actually how the system evolves to another state at time t2. So at this point, with Newton's three laws, we can follow a system completely. As it evolves from a state 1 at time t1 to a later state, a state 2 at time t2, at a later time t2. Well, we'll see. I guess it's clearer. So clearly t2 is greater than t1. All right, and so we have a luxury of knowing exactly how the system will unfold, how it will evolve. And so we come out of Newton's laws feeling quite powerful, that we can really have complete control and can predict the mechanical system. And so far we have 3 out of the 4 laws or principles that are the underlying principles of mechanics. But the question is everything really that happy? I mean, do we really have that much understanding or that much control to completely understand and characterize the system? And the answer is, well, is applying Newton's second law ever too hard? I mean, that's a big question. So, I should say is it ever too hard to apply Newton's laws? Why I can't write? We have Newton's 3 laws of motion. The first law is the law of inertia. An object in motion or an object at rest tends to stay at rest unless acted on by a force. And an object in motion at constant velocity will tend to stay in motion at constant velocity unless acted on by a force. That's the law of inertia. Newton's second law is the mathematical statement: sum of all forces is mass times acceleration. And from Newton's second law depends on the understanding of the concept of inertia. So we go from inertia, now we define forces, and then Newton's third law deals with interaction, action-reaction couplet. For every action, there's equal and opposite reaction. So the normal force is an example of a third law force. All right. So again, you know, we've had great success so far in applying Newton's laws, but is it ever too hard? Well, I have a, you know, so again, I'm just kind of briefly synopsizing what I say in my lectures anyway, but let's consider a two-body problem. So two-body problem, you know, and what is a two-body problem? Well, it's two bodies with a mutual interaction or a mutual force of interaction. So it could be, you know, it could be very well be, let's say we have the sun and we have the earth. And what's their mutual force of interaction? Well, the force of gravity. That's an example. Or it could be, you know, some positive charge plus Q and maybe negative Q. And again, there's an electric force. Two bodies with a mutual force of interaction. We can do this all day. We have no problem whatsoever. We've done gravitational problems, no problem whatsoever. We can do this. So we can do this problem. This problem can be solved analytically. And when I say by analytically, I mean with pencil and paper and getting a closed form solution. All right, so we can solve this. We can solve a two-body problem analytically. No problem at all. Pencil and paper, no use of a computer. We can do this. All right, well, let's consider complicating things a little bit more. Let's throw in a third body, three-body problem. So throw in a third body, maybe the moon. Okay, so now what do we have? Well, let's say in this particular case, we have a force between, let's say, the Earth and the moon. We have the force between, say, the Earth and the sun. And, you know, there is a force, say, between the sun and the moon. So three forces, three bodies, mutual forces. Can this problem be done analytically? And the answer is no. So a three-body problem cannot be done analytically. Too many variables for the number of equations. So already it gets too hard. So thanks for playing. You can't use, I mean, you can't solve this with analytical. You can't solve this analytically in Newton's laws. Too hard. What might you do? Well, you could write a computer program. You can even do this possibly with even Excel. And so, you know, so there's a way of getting around this. You can, you know, you can take steps in time and every single step in time, you figure out, okay, where's the moon, where's the earth, where's the sun? Let's get the forces, and let's figure out, okay, what, you know, due to those forces, apply Newton's second law. What acceleration is each body going to feel? Let's take another step in time and kind of step through time and see how, you know, how the system changes. I mean, that's possible. Can't do it analytically, but you know, you could write a simple program. I could write a program in 20 minutes to model this. Okay, well, what about 10 bodies? I could still do it. It becomes hard. What about 100 bodies? Well, that starts becoming really challenging for the computer. You know, we have all these interactions. You know, for every body, you have to think about there being each and every one of those bodies each one has a pair. Each pair has some sort of interaction. What about Avogadro's number of bodies? No way. No computer in the world can solve that problem. So again, even if you could go and use a computer program, you still run into a brick wall. So the question is, as I've just kind of shown you, it becomes readily difficult, or maybe even impossible, to apply Newton's laws. You also have the situation of the following. You also have, look at Newton's second law. Sum of all forces is mass times acceleration. Okay, well, the right-hand side, not a problem. I mean, again, I could figure out the system mass. I can find the acceleration. We did that with chapter 2, chapter 3, Galileo. The problem really is, can you resolve all these forces? Is it possible to resolve all the forces all the time? And in some cases, it may be too difficult to solve all the forces. So again, even the solution of Newton's second law possibly is too hard to do because of the left-hand side of the equation. Do I know these forces? How well do I know these forces? So we go from having this great feeling of power to be able to solve anything, and to be able to not only tell you how to get from state 1 at time t1 to state 2 at time t2, but I mean, I know how the system transpires. I know how the system evolves from t1 to t2. Now all of a sudden, we go from a state of great confidence to a kind of a state of desperation. Is there any way I can reach state t2? You know, so I have state 1 at time t1, and I have state 2 at time t2. And I want, you know, whatever my system happens to be, I want to somehow, I mean, I may be able to completely characterize the system at time t1, but I want to be able to characterize the system at time t2. So what I'm looking for is anything at all that I could possibly know about t2 that can get me from one state to the other. Anything I could possibly understand. And so the question is, well, is there anything I might be able to know for certain about the future? Is there anything I can know for sure about the system at a later time t2? Know about the future? And the answer really is, well, is there anything that is constant? And so we look far and wide, you know, try to find, is there anything that happens to be a constant? Something that I can calculate at state t1, and I can later calculate it at state t2 or state 2, and it is the same. And long search, you know, for whatever, anything I can say, and it turns out there is a special value, and that value is called the energy. So the energy is a number that I can calculate in the system at t1, time t1. Let the system evolve. And then calculate it again at a later time t2. And this number is the same. It does not change. And in fact, that is the definition of energy. Many people, as I've said in my lectures, people use the word energy all the time. I have an energy bar, I have an energy drink, I have a lot of energy. We have a department of energy, but what actually is energy? And most people don't know. This is what it is. All energy is a number that you calculate in a system at time t1. You let the system evolve, you calculate that number again at a later time t2, and that number is the same. That is all the energy is. Now, pretty much almost every textbook I've ever seen goes about, including Cutnell and Johnson, and including OpenStax. They go about, in my opinion, introducing energy kind of backwards. They say, well, they make the assumption, well, students are going to assume energy is important because it's always talked about. And so they go into saying, well, we got this one kind of energy called work. And then we can go from work to kinetic energy. And then we can go from potential energy. And we can go through all kinds of different kinds of energy. And finally, we talk about the conservation of energy. I can tell you right now, there's a lot of things that people talk about, but they're not necessarily important. You look at reality TV, for instance. I mean, people talk about it all the time, but is it really that important, right? So in a way, it's kind of a dissatisfying thing a lot of physics textbooks do. And really what the first thing they really ought to do is say, this is what energy is. This is the plight that you have, that you can't solve a physics problem because you can't apply Newton's laws. What do? Well, you find a line from state 1 to state 2, and your lifeline is energy. It's this number that happens to be conserved, and it happens to take many forms. Right? So that's really what energy is. That's the only reason why energy is important. That's all that it is. So energy is nice, and it is a scalar. So, I mean, we deal with a lot of vectors like forces. Well, energy, what's nice about it, it's a scalar. It's literally just a number like you've been using since your days in elementary school. So energy is a scalar. And the principle that I just got done talking about is called the conservation of energy. So again, what we just got done talking about and what this lab is about is called the conservation of energy. It's a fancy way of saying that I have this number called energy. I calculate it in a system at time t1. I let the system evolve, and then I calculate this number again and for the same system at a time t2, and lo and behold, that number is the same. That is that's a fancy way of saying conservation of energy. So yes, energy is a scalar, but the problem with energy is, yes, it takes many forms, but conservation of energy is very hard to apply. I mean, in general, you almost can't really apply it. So again, conservation of energy, and I just got done saying energy is a scalar, which is nice. It means I don't have to go and make, have vector components, cosines and sines and everything else. It's just a number. But, energy takes many forms. And in fact, during a problem, it transforms one form to another in a single problem. And we'll see that today as well. So what are some forms of energy? Well, we have work. I mean, I'm not going to go into, again, the lecture goes into details about all these various types of energy, but we have work, we have kinetic energy, we have different kinds of potential energy. We have gravitational potential energy, like we talk about today, but we also have potential energy with a mass and a spring, like Hooke's law. There's different kinds of potential energy. You have radiant energy, you have heat. Later on, talking about thermodynamics, you have heat, you have radiant energy, you have sound energy. Right? So again, you have all kinds of different energy. The issue with energy is a lot of the kind of energy that you have actually leaks out of your system. All right, so we have two kinds of, so we have two kinds of forces, as I've talked about in the past. And forces, you can actually link forces to work and work to kinetic energy. But we have two types of forces. We have one force called a conservative force. And we have another one called the non-conservative force. Okay. A conservative force is one where the work only depends on the endpoints. And not the path taken by the particle. Path independent. So for instance, if I want to figure out, let's say, so gravity is gravitational force is an example of a conservative force. So let's say I have my cell phone. It has a weight. Now I'm gonna go and I'm gonna say, okay, where I have my cell phone right now, I call that the zero potential energy, or I call that, I call that, I haven't moved it at all, but I'm gonna go and move my cell phone up. I'm gonna have an upward force of my cell phone, and I'm gonna move it up. It's gonna be a distance y, and I'm essentially the force that I'm applying, even though gravity, I'm fighting against gravity. We're going to say that I'm moving it at a constant velocity. So the force that I'm applying with my hand is straight up, and the displacement is straight up. And so, as we know from class, we know that the work will be just mgh. And it doesn't matter if I move my cell phone straight up or I move in some zigzaggy pattern. All it really matters is at some point I have raised my cell phone by an amount y or amount h. And it doesn't matter what path I took to get there. So if that's the case, that gravity is considered a conservative force, or any other force. Electrostatic force is also a conservative force. You'll learn about that in physics too. Conservative forces have a corresponding potential energy. So if the force is conservative, there is a corresponding potential energy. If the force is non-conservative, it does not have a potential energy. Okay, so conservative forces, so gravity, there's such a thing called gravitational potential energy. We say, potential energy, gravity. Again, go to my lectures to see the details, but it's mgh. If I'm raising, say, an object from, say, the zero of potential energy to a height h. I'll go and raise it from a height h. Maybe it used to be down on the ground. I've raised it to a height h, and I've applied a force against gravity, mgh. All right. There's another potential energy, the Hooke's law force. The Hooke's law force is also a conservative force, the mass and the spring force. It has a potential energy as well. All right, so any force that is conservative has a corresponding potential energy. It's very important to this problem. Now, if a force is non-conservative, it does not have potential energy. Non-conservative forces either add energy to the system or subtract energy from the system. All right, so what's an example of a non-conservative force? And one's friction. Friction is a force that does depend on path. So again, non-conservative forces add or subtract energy from a system. So in the case of a conservative force, again, it doesn't matter, like, here I have my cell phone, let's say it's zero potential. I can go up, I can recover the whole system just by lowering my cell phone again and put it exactly where it was before I ever moved it. Okay, I can actually do a reversal path, and I can actually recover the entire universe as I had it before. Okay, I can take the whole thing and do it backwards. That's what I can do with a conservative force. Non-conservative force versus friction. If I sit there and rub my cell phone on the ground, and I rub it on, I rub it and then I rub it backwards, I'm not undoing what I did. Rubbing it backwards is just going to do what? It's going to dissipate more energy. I can't just go backwards on a non-conservative force or regain the universe as I had it before. All I'm going to do is just dissipate more energy. Oftentimes it's given off as thermal energy. It's kind of like anybody ever watched Ferris Bueller's Day Off. You can't just take the car and put it in reverse, get the miles off, right? I mean, it's one of those things that you can't. There's no such thing as just reversing a non-conservative force. All right. So any way you look at it, anyway, and it's path independent. If I decide to move my cell phone in the straightest, shortest path, I'll dissipate less energy than if I move into some zigzag path. Again, more rubbing I do, the more energy is given off in thermal energy. All right. So why is that important here? Well, when we talk about applying the conservation of energy, the conservation of energy applies in mechanical systems if all forces involved are conservative. And what you can say then, if that's the case, then you can literally say that the kinetic energy at some initial state, call it I, plus the potential energy at an initial state, call it I, is equal to the kinetic energy at a final state, say F for final, plus a potential energy at a final state, say F for final. And they all equal a total energy E. So anytime throughout my system, I can add up the kinetic energy plus potential energy. It'll be the same value. It can be done at an initial state. It can be done at a final state. It can be done at any particular time. I can use this particular equation, this principle, to solve physics problems. I can know about a final state because I can say, okay, well, my initial state, I know these two energies must add up to a total energy, and that total energy must be computed all the time for any later state. All right, and so I can use this to solve physics problems. This is your fourth and final principle that underlies the theory of mechanics. There are 4 laws of mechanics. All of mechanics, bodies in motion, the study of bodies in motion, rely on just 4 principles. Newton's 3 laws of motion and the conservation of energy. That is all you need to do the entirety of mechanics. Everything in mechanics is an application of 4 principles. Okay, now what happens if you have a non-conservative force like friction? What happens to this now? What happens, well, is as you realize that, in real life, you're going to realize that, okay, I have my, let's say I have, some sort of a pendulum clock or something that I don't, any kind of pendulum clock you may buy has a little kick, something that's always kicking it, keeping it going, kind of like you're pushing a child on the swing. Every single time the pendulum comes back or whatever, it gets a little kick to keep it going, right? Well, you'll find out if you didn't have that, then what would happen? Well, you would add up the kinetic energy plus potential energy, and you find out that at a later time, you add these 2 numbers up, and then this quantity on the right-hand side becomes less. Something is depleting your energy. So I need to put another term in. And so that term becomes the non-conservative work. The work done by non-conservative forces. So when I have non-conservative work, now my conservation of energy equation looks like this. I have the, I have kinetic energy initial plus potential energy initial plus work non-conservative. And that's equal to kinetic energy final plus potential energy final. So you wonder, hey, what happened to my energy? Well, it was depleted by this term. Something is either, and it could very well be that something's adding energy to your system. But the whole point is, PE sub KE sub I plus PE sub I is not going to equal KE sub F plus PE sub F. Either this term is either the energy is being added to your system, or in many cases or most cases it's being deleted or depleted from your system. Okay, so that's what we're going to talk about tonight. We're going to talk about this conservation of energy principle in this lab. All right, and so I have the lab fired up right now, so let's take a look at it. It's a fairly short lab, it's about 2 pages. So let's I have it up, so let me see how hard this is. Okay, so I've already kind of went through the point of clicking on the link. So let me share my screen. Okay. You know what? Already fired it up. Here it is. All right. So what you'll notice so do you see this person on the skating on the track?
Yes, I do.
Awesome. Okay, so what we have is a skater going back and forth in this track. And what we want to do is we want to kind of answer some questions. And so we see this track right here. Let me reduce this here. All right, so what we want to do is let's see, we want to do a few things. I'm going to move this over. All right, we want to first of all click on this what's called a potential energy reference. It's a little dashed horizontal blue line. Now, as I said before in the lectures and stuff, the potential energy, the only thing that matters regarding potential energy is its difference. And so you have the freedom of setting what we call the zero potential energy however you like. So one of the things I would probably like to do here in this lab is say, move this blue line, if I can actually select it. Move this blue line to, all right, having trouble. All right, so this thing's being stubborn. All right, here we go. I'm gonna move this blue line to right at the bottom of the track. All right, so when the person gets to the bottom of that track, he has zero potential energy. And so we know that, as you're watching going back and forth, he goes up the one side of the ramp, stops temporarily, goes through, the middle, goes up the other side. When he's stopping temporarily, he has the maximum potential energy, zero kinetic energy. And when he's at the very bottom of the path, he has zero potential energy because he's at the zero potential energy, and he has maximum kinetic energy. We can actually do is what I'm going to do here too is I'm going to double check here on track friction. Okay, so I'm making friction this minimum, so friction is 0. We're on the Earth, so we have the ability to go to Jupiter, the Earth, or space. Gravity on the Earth is taking me 9.81 meters per second squared. Actually, we can hypothetically go to the moon too. And let's see, what else do I want to do? I want to actually show the energy versus time. Actually, let me do that in a minute. I'm gonna stop him. So I'm gonna hit the pause button, and I want to actually make the skater go as slow as possible. So I'm going to slow him down. Right now he's going too fast. I don't have that kind of reaction time. and I'm going to select what's called, I'm going to say return skater. Return skater puts the skater right at the top position of that he's going to take for kinetic energy, for potential energies. So that's at this point, the skater is going to have the maximum potential energy. Potential energy is again an energy of configuration. It's an energy that he has because he's at a certain position in a gravitational field with respect to what I'm referring to as the zero potential energy. It's an energy of configuration. Now, we're going to do now is we're going to also open up energy time graph. So I have a little real estate problem here on my little laptop. So I'm going to kind of put this off in the ground here. So at some point, you're not going to actually see the skater in the right hand half of this. You're not going to see the skater because I want you to see the graph as well. So I'm going to also clear the graph. I'm going to select clear. And I also want to, let's see here. Okay, notice, okay, so now, right now, notice that the potential energy is reading what? Is that 2,632.02 joules. Kinetic energy right now is reading 0. Okay, so we want to kind of make a note of that. So I'm going to put this on my whiteboard. Again, you can't see my whiteboard at this point, but my initial potential energy, the way I'm looking at this right now, is going to be, again, I'm writing this on board. You'll see my board in a minute. 2632.02 joules. You see that on the display?
Yes.
Kinetic energy, he's at rest. Kinetic energy is 0. Now the total energy, you'll notice, I mean the thermal energy, I turned off friction, so there's no thermal energy. And if you have friction, you're going to be dissipating heat. I'm not interested in that right now. I'm just interested in trying to save energy is conserved. Notice the total energy is exactly the same as potential energy. Why? Because the two add together right now is 0 plus 2632.02 is equal to 2632.02, right? Now, I'm going to release, I'm going to say go. And again, I've slowed him down. You'll notice that the energy is, the kinetic energy is maximum, the potential energy is minimum, and vice versa. But notice that they always add up. The green line is total energy. That's always a constant. And this skater is going back and forth, dissipating no energy. The energy, kinetic energy, potential energy is sloshing back and forth, always adding up to the same constant. So when the skater's at the highest part of the path, he temporarily stops. That's where the potential energy is maximum, kinetic energy is the minimum. When the skater's at the very bottom of the ramp, he has all kinetic energy. He's lost all the potential. All the potential energy has been converted to kinetic energy, and this is going to go on forever. I have nothing in it to dissipate. So I could sit there and watch this all night long. Nothing's going to dissipate it. All right. So again, you're seeing energy being conserved here because I don't have any non-conservative work. I've turned off friction. The only force that's in play right now is gravity, and that's conservative. And so I'm able to apply the conservation of energy all day long. All right. So I'm looking at number 1 on the front page, first page of the lab, and it says sketch the track and label the following positions. The skater has maximum speed. The skater is stopped. The skater is going his average speed. The skater is going slow. The skater is going fast. All right. So let me stop sharing for a moment. I'm going to pause this, and I'm going to stop sharing. Let's go back to the whiteboard. So what I want you to do, and I'm going to see if you can help me out here, Sarah. It wants to, all right, so again, 2632.02 is the value that I care about. So I'm going to keep that on there for a moment. All right, let's sketch this thing as best I can do. Again, I'm not an artist. It looks like something kind of like this. All right, that's actually that's pretty good for me. All right, so we have the ball, we have these positions that you see labeled and the high points, and you have the bottom of the bottom of the path right here. Now, of course, so part A says what? The skater is at its maximum speed. So that's A. Skater's at its maximum speed. Where do you think I should where's the skater? Where's the skater at its maximum speed, you think?
Would it be like halfway between the first point and the bottom point kind of area?
So remember, the kinetic energy is equal to 1/2 mv squared. So where the kinetic energy is maximum, the speed will be maximum. So you notice that at either of these endpoints, he's temporarily slowed down. He speeds up. He goes as fast as speed right here, and then he starts slowing down again, stops, starts speeding up, fastest speed right here at the very bottom. And again, he comes back and does all this, right? This is the zero potential energy on it. So what this means is that the two energies, the kinetic energy plus potential energy, must always add up to the same thing. You're going to have E, which is going to end up always being this number, is always the kinetic energy at any point plus a potential energy at any point. So at these endpoints, the potential energy is maximum. So the kinetic energy is 0. Now, the kinetic energy, of course, it's going to be some sort of mgy. Now he has a certain mass. Actually, the mass is 75 kilograms. I'll show you that in a moment. But right here, mgh is the maximum potential energy. By the time the skater gets down to this very bottom of the trough, all of that potential energy has been converted to kinetic energy. So the maximum kinetic energy is right here. All the potential energy is gone. So the kinetic energy is entirely equal to this number. So your maximum kinetic energy, I put a little a, is at the very bottom of this trough. So that's going to be where it's going to be going fastest. Why? Because the kinetic energy is 1/2 mv squared. The maximum kinetic energy occurs when the velocity is max. Mass doesn't change. So the velocity is max, the kinetic energy is max. So A asks you, where's the skater at its maximum speed? I drew this picture, put a little A right there. That's where the skater has its maximum speed. Is that because the skater has a maximum kinetic energy there? Where's the skater stopped? Where do you see the skater being stopped? What do you think?
I guess like from his starting position, and then when he goes down and past his fastest speed, and then when he gets up, I'd say by your like mgh kind of area.
You're absolutely right. Yep. So he's temporarily stopped where he has the maximum potential energy. So all the energy, the maximum potential energy is equal to the total energy. And when he's at the very bottom, the maximum kinetic energy equals the total energy. The two numbers always have to add up the same thing. And sometimes the one of the numbers is the energy of the system is entirely that number, but everything has to add up. So altogether, what you're going to find out is your total energy always must equal 2632.02. Sometimes it's entirely kinetic and 0 potential, like right here. Sometimes it's entirely potential and 0 kinetic, like in these places. And when that happens, again, kinetic energy is energy of motion. We have no motion, you have no kinetic energy. C says the skater is going his average speed. So I would say the average is kind of somewhere in the middle between A and B. Here's the max speed, here's 0 speed. I would say right around here would be average. And everything's symmetrical. I put little C's there. The skater is going slow. Well, slow would mean that, here he's stopped. Here I'd say the skater is slow. And also here, he's, as he's coming down, he's slow. And then he finally gets faster. He's fastest right here. Then he starts slowing down. I would say right before he hits B, he's slow again. and it comes back down. So again, I would say E, A, B, C, D. I'm sorry, D, right around here, I would say he's slow. Skater's going fast. Well, again, fast would be, you know, pretty close to where he's fastest, right? So I would say probably around here, label. All right. So again, it's qualitative. I mean, there's no real numbers here. You're kind of sketching this out, and you're just trying to understand how the motion, you know, how this periodic motion is occurring. So that's really what we want on problem 1 and on the front page. Okay, so now the question comes down to is, okay, well, we want to know what is the speed of the 75 kilogram skater at 2 seconds. So again, let me share my screen again. I didn't show you something. Let me share again. So another thing you can do, whoops, that's not what I want, sorry. Here, all right. Another thing you can do is you can look at, someone's gonna kill this for a minute. You actually can look at, you can hide friction. Okay, so friction is right now set to 0. I can edit the skater. And what you mean by edit the skater, so you can see this, you can see the software again?
Yes.
Okay, edit the skater, you notice that its mass is 75 kilograms. Now that's the default mass. So anyway, I'm not going to change that mass. But so the idea is, okay, well, we want to know what's the speed of the skater at 2 seconds. All right, and so what I'm going to try to do, I'm going to kind of do this a couple different ways. Let's see if we can theoretically predict it. Well, actually, let's just kind of find out. Okay, let's see here. We want to find 2. Number 2 is what's the speed of the 75 kilogram skater at 2 seconds, and what's the height of the 60 kilogram skater at 2 seconds. All right. So what I want to do is I'm going to go back to the software, and I want to try to set it up and slow everything down. So I'm going to return the skater, and again, 75 kilogram skater. There he is. Again, I want to slow everything down, so I'm going to put it at the slowest possible speed. I want to open up the energy time graph again. I'm going to clear it by hitting clear. Okay, and again, you know, the horizontal axis is time. I'm going to try to stop this thing. So again, as you notice, again, that special number 2632.02. I'm going to try to find out what this looks like at what is the energy predicted by the software in 2 seconds. So let's see how well I do. Hopefully it goes slowly enough. I'm going to try to see if I can stop it right at 2 seconds. I did not succeed. All right, let me try that again. Hang on 1 second. All right, back to return. So return the skater. Why it wants it. Okay, I want you to go slowly. All right, try this again. All right, energy time. Coordination is not my strong point here. All right, so here we go. Try to stop it at 2 seconds. All right, nice and slow. Good, I like that. That's not quite 2 seconds. It's not either. There you go. That's probably as good as I'm going to get. All right, so at 2 seconds, I see the kinetic energy according to this according to the software, the kinetic. So again, everything still continues to add to, I'll show you my whiteboard in a second. The total energy is still 2632.02. But the kinetic energy, the reading is 500.48 joules. And the potential energy, and this is at 2 seconds. Again, this is at t equals 2. I'll show you my board in a moment here. I'm just writing this stuff down. It's 2331.53. So hypothetically, those add up. So the question is, all right, so we have this. So let me stop sharing. All right, so I wrote those numbers down, as you can see. Now, so the number 2 is asking me, what is the speed of the 75 kilogram skater at 2 seconds? Well, at 2 seconds, we know that the kinetic energy is a 1/2 mv squared is equal to the kinetic energy. Okay, so we want to solve for v, right? So we're going to multiply both sides by 2, divide by m, take the square root. So 3 steps of algebra 1, we have 2 times the kinetic energy divided by m. And we take the square root of that. All right. Now, what is that? Well, let's see. We can convert that. We know the kinetic energy, so it's going to be 2 times. Again, I want you guys to do this experiment on your own. So you'll have a different number than me. Slightly, should be close, I think. The mass we're told is 75 kilograms. All right, and so we'll take the square root of that and plug it into my calculator and find out what I get. All right, 500.48 joules times 2 divided by 75. Take the square root. I get 3.65 meters per second. So in 2 seconds, it has gone from 0 meters per second to about 3.65. All right, and so that's what I get. Now, again, you'll have a different number than me, but again, it's going to be based upon what? It's going to be based upon whatever your kinetic energy reading is. All right. Number 3 on here. What height is the 60 kilogram skater at 2 seconds? All right. So now, I don't know if that's a typo or what, but we'll kind of go with it for right now. If the skater is 60 kilograms, right? We'll kind of answer the question, even though, well, let's do it. Actually, you know what? Let's do it for 75 kilograms. So again, anybody paying attention to the lab, to this, I think number 3 is a typo here. I think we want 75 kilograms. I realize that. So let's change that to 75. Let's see if I actually have my pencil with me here. All right, so again, number 3, for number 3 on the front page, the mass is 75 kilograms, all right? So again, let me write this down to make sure I clarify this and broadcast it. So for number 3 on front page of lab, use mass equals 75 kilograms. Okay, I think 60 was a typo. All right, now, if that's the case, we want to find the height. What do? Well, we use the potential energy formula, right? So again, the mgh is the potential energy. And we'll make sure we understand that it's gravitational potential energy, mgh. I'm just kind of writing, I'm solving for h, that's why I wrote it this way. want to solve for H, right? What do I do? I divide by mg. So H is going to be the potential energy that I read off my software divided by mg. All right. So again, I'm on Earth here, so I have 2331.53 joules, and that's divided by the 75 kilogram mass, and that's divided by on Earth, so that's 9.81 meters per second squared. Okay, so for my particular example here, I have 2331.53 divided by the mass, 75, divided by G, 9.81, 3.17 meters. So above, so at 2 seconds, I expect the skater to be about 3.17 meters above what I'm declaring as a zero potential, or 3.17 meters in height above the bottom of this track. So now number 4 says, what is the kinetic potential and total mechanical energy at 10 seconds? All right, and so again, all you're really going to do is what? It wants you just basically to go to 10 seconds. So all you're really going to do is run the software. All right, and so again, this let me share again. I mean, this is a very software-oriented lab, unlike a lot of the previous labs. This one does very much rely on the software. So what am I going to do? Well, I'm going to continue, and I'm just going to run it and let it do its thing. So I'm at 2 seconds. Let me try to run it and then stop it at 10 seconds. All right, let's see if I so you notice he's going back and forth. You only see about half his picture again because I have a little real estate issue. All right, so we're sitting around almost, we're passing 6 seconds, 4 more seconds. Again, this is the simulation. These are seconds in simulation time, so these are not seconds in ordinary time. Let's make sure I am ready to kill it. Okay, 9 seconds. All right, stop. Not quite. Yeah. All right, I think that's pretty close. All right. All right, so what do I have? Well, what would you write down in this case? Well, again, I want you to do the lab yourself, but you'd write down the kinetic energy is, what does that say? It's, well, the potential energy is 1959.87. I don't know if that's an 8 or a 3. I think it's a,
Kinetic energy, I think, is 872.14.
yeah, yeah, I think that is the case too. It's a really bad bad font. But anyway, yeah, you write that down. And of course, the total energy is what? 2632.02 again. I mean, again, that's a constant. So the idea here is that the energy is going to, the kinetic energy and potential energy are going to change. The total energy is going to remain constant. Why? Because the only force involved is a conservative force called gravity. Now, what it wants you to do next, and I'll let you, the student, do this, but what it wants you to do next is to repeat questions 1 through 4, basically do what we just did, but do it for the moon and didn't do it for Jupiter. And so what are you going to do? Well, you're going to essentially do everything we just got done doing for 1 through 4. Again, you're going to work this all out on a separate sheet of paper that you're going to turn in, our separate papers that you're going to turn in with the lab. But notice that right now it's set to be the gravity set to be the Earth. Well, you do the moon. You have it be at the moon there, and then you notice that the gravity is 1.62 newtons per kilogram, meters per second squared, so it should be. And then you have Jupiter, and Jupiter is it's going to be a lot larger, 25.95. And then eventually we'll go to space, and space is 0. All right, so you're going to do all the same kind of computations, the exact same things we just got done doing for 1 through 4, but you're gonna do it for the moon, you're gonna do it for Jupiter. Okay. Now, we're going to, and also there's an explanation involved. Explain why the results differ between the Earth, Moon, and Jupiter. So maybe I'll discuss this a little bit, what your results will be. So you notice that you're going to do a couple of calculations. So let me kind of go back. Let's kind of review what we just got done doing. And you're going to see different results. You're going to want to explain why your numbers look different. All right. And so, well, what did we do? Well, let's see here. So we are going to have a few differences. All right. And that is, well, what do we know? We know the total energy is always going to be kinetic energy plus potential energy. We'll put a little G for gravitational. And we can say that any given point, if you have the horizontal dashed blue line indicating the zero potential energy, wherever you happen to be, whether you're on the Earth, the Moon, or Jupiter, there's going to be some height h that's going to be above that blue line. You're still going to be on the same track, right? And you're still going to have a 75 kilogram mass. Again, your mass is a characteristic of the body, right? So mass is going to remain 75 kilograms throughout. Again, that's a whatever your mass happens to be as a person, that's the same mass you'll have on the Moon or on Jupiter or anything else. What's different is going to be your weight, because gravity is different, right? And so you'll notice here that the total energy is going to be 1/2 mv squared plus mgh. So you'll notice a different total energy. On the Moon and on Jupiter, due to a different value of G. So a different value of the gravitational acceleration. All right. So again, when you're initially in your initial position, all of your energy in your system is what? It's gravitational potential energy. Well, in that particular case, it's mgh. Well, you have the same m, you have the same initial height, you have a larger or smaller g, which means that the total energy that's going to be in your system is no longer going to be 2632.02. On Jupiter, that number is going to be bigger. Why? Because G is bigger. And on the Moon, it's going to be smaller because G is smaller. So the total energy, again, initially, you have no kinetic energy. Initially, when you're in an initial configuration of the system, all of your energy is potential energy, and that potential energy is going to calculate to be a larger number. And this number always has to be the same. So what that means is that if you have a larger amount of total energy, that means that your maximum velocity is either going to be larger, like in the case of the Moon, or smaller, larger in the case of Jupiter, or smaller in the case of the Moon. Why? Because there's more energy in your system. There's more energy in the system. So you'll notice that, okay, so first of all, you'll have a larger amount of total energy. Why? Because G will be bigger on Jupiter or smaller on the Moon. And so what that means is that at some point, when you're, at the bottom of the ramp, where the kinetic energy is maximum and the potential energy is zero, kinetic energy will equal the total energy. Well, the total energy is bigger. Why? Because because G is bigger, right? I mean, again, initially in the whole problem, there was no kinetic energy. So you've set the total energy to be a larger value because G is bigger if it's Jupiter or smaller if it's the moon. So there's more energy in the system. And when all that energy is converted to kinetic energy, you're going to have a larger speed if you're on Jupiter, or a smaller speed if you're on the moon. All right. So again, on Jupiter, Ke max is greater than on Earth. On the moon, Ke max is less than on Earth. All right, so again, the equations that you end up calculating, you're going to have a larger Ke max. So again, when you calculate those same equations that I just got done computing, all right. And so for instance, I did, what was it, number 2. I want the speed at 2 seconds. Well, any corresponding speed is always going to be greater on Jupiter than on the Earth, and any corresponding speed will be less on the moon than on Earth. So again, when I calculate V equals 2 kinetic energy divided by m square root, I mean, the kinetic energy on Jupiter is going to be, point by point greater than would it be on the Earth. You're always going to have a larger velocity. Why is it greater? Because there's more energy in the system. The kinetic energy on the moon will be less, right? And of course, it'll be even more apparent when you look at the height. Again, what's that going to be? Well, it's going to be the potential energy divided by mg. So, for the same energy, the height's going to be smaller because of g. So again, it's you're given heights. You're going to have a different value of height. Why? Because of gravity. So again, I want you to explain that to me. So you'll change these. You'll change to Jupiter and the moon. Basically do exactly what I did, but you'll explain. But I want you to explain to me why you're going to see values that are different. You're going to do the same experiment. You're going to see different values. Why is that? So again, I kind of told you why. I definitely told you why. I mean, is that clear?
I got it.
Awesome. All right, so 1 through 4, it's kind of like really 12 steps, even though it looks like 4 steps. All right, so again, it's repeating. All that's going to be put into corresponding. Again, you're going to turn it in as additional pages to the lab. All right, let's look at number 6. Again, I'm on the bottom of page 1 of the lab. So number 6 is giving you a little different view. And so I'm going to try to draw it. Again, we're going to kind of look at this theoretically. And so maybe not exactly what things look like in the lab, but so we have different little points that we're looking at here. All right. All right. So in this particular case, again, everything only depends on basically where something is in the gravitational field. So we're going to take the lowest point. The lowest point is this left trough here, if you will. So that's the minimum. That's the global minimum, as we call it. And so I think the best thing to do is call this 0, of potential energy. And notice that I think this may be a little bit higher, but the thing is you're gonna start off, your skater is gonna start off like over here, and you're gonna have you're gonna start off at rest, you're gonna have maximum potential energy in the system. So start off at rest, that's maximum potential energy at this point, zero kinetic energy. It's going to convert all of its potential energy to kinetic energy, and it really should maximize about right here because it's at the zero potential. It's going to rise up, but not as high as it was initially. So it's still going to have some kinetic energy, some potential energy, and then it's going to come down. It's going to reach a minimum that's not as low as a zero. So right here, even though this is a minimum, there is still some sort of maybe an H2 or something right here. So all of its kinetic energy is not converted. There is still some potential energy here, and then it's going to come back and climb and lose its it loses all of its kinetic energy again to maximum potential energy. So the question really comes down to this track is called the double well, and in fact there is you can play around with the double well if you like in the lab, but I kind of look at this theoretically. I mean, we've kind of seen the skater already. So one of the things I want to know is, okay, the skater is at its maximum speed. So I'm going to ask this question: where do you believe the skater is going to be at its maximum speed? Where should I draw A? Right? Where should I write A?
Would it be when he's first down?
Yeah, the bottom of the lowest well.
Yep, right there.
No
then,
potential energy, all kinetic energy. So your A wants maximum speed, and only has a maximum speed at one point. There it is.
Yeah.
This is not the maximum speed. Why? Because here it's zero potential energy. Remember, total energy must always add up to be the same. So it's always going to be some kinetic energy plus potential energy. Well, up here, he has all potential energy, zero kinetic energy. So the potential energy is equal to the total energy. Down here, and only down here, he has zero potential energy. So all the energy in the system, the total energy must be all kinetic. So again, kinetic energy, as we recall, is given by the formula 1/2 mv squared. So the maximum kinetic energy occurs at the maximum speed. All right. So again, the maximum speed is going to be only right here. Where is the skater stopped?
Would it be when he goes up at the end?
Yeah. So in the beginning, where I'm drawing him right now, he's currently stopped, and again, he's not stopped here because there is, again, the potential energy is not maximum. The two numbers must add up to the same, so there has to be some kinetic energy at this mountaintop. And so the only place where he stopped is wherever the kinetic energy is maxed out at H. So wherever H is here, if it's the same H, he would also be stopped right here as well. Again, this is the case where all the energy is now potential, and there's no energy left to be kinetic. And the two always have to add up to the same total number. The skater is going at its average speed. Again, I would probably call the average right around midway between A and B. And so I'd probably say its average is, say, here. I would actually probably say the mountaintop here is probably an average speed, and probably around here too. I say all three of these locations, I would call him about average, right around the middle. So here's the mountaintop of this smaller peak, and here I would estimate his speed to be right around his average. Why? Because there is potential energy, nowhere near as much as the maximum. So, and then I would say it's about the same height as what I would say would be the midpoint between the top and the peak here and the bottom of this deepest well. All right, D, skater is going slow. Where do you think the skater is going slow?
I would say after the first A, after your first A when he's going up.
First B, you mean, right?
Yes, sorry.
Okay, yep. And right before, right below this other B. So I would write.
There you go.
What's the next letter of the alphabet here? D.
Yeah, there you go.
Here and about here. And again, skater's going fast. I would say fast would be, I would say he's going fast here for sure, because he's going right near his fastest speeds. I'd say E here and right after. And I probably would indicate this area is pretty fast as well. I probably put some E's right here as well. Right around these troughs. I mean, this peak, I mean, this valley is not as low. This well is not as low as the global minimum. But I mean, again, this is fairly low, and I would say that this skater is going. I would call, again, it's all qualitative. I would say qualitatively, I would refer to right around the bottom as well as fast as well. And in fact, maybe I would even refer to this as fast. All right, that ends page 1. Page 2, number 7, sketch the energy position graph and label where you think the same 5 positions in the prior questions are. All right, so I'm going to try to do this. All right, so he has a picture here. I can't leave myself a lot of space, but I hope I'm entirely on the whiteboard here. So as you can see, try to recreate this. This is the total energy, which is constant. And you notice that the kinetic energy is lowest right here. It goes up to a max, down. Yeah. 1 second here. And I'm trying to recreate this, or is not a strong point. All right, let's turn it down to about half. Trying to do it with the picture as well. Come back up. Go back. And then potential energy likewise is going to start up high. Go to its a minimum. It's going to go up. It's a good place to have multicolored pens. I'll label the high. So this graph is potential energy. You can follow with your eye. And this graph would be the kinetic energy. All right, so I kind of drew it in an obvious way, the best I could, to kind of correspond with the picture of the double well. And so I want to go back and label things according to here. So again, this straight line is total energy. Hope this is clear. And this line here, if you follow it, is the potential energy. And this other line, if you follow it, is the kinetic energy. Again, I should use multicolored pens here, but maybe I'll do is I'll make this one dashed. All right, so the dash line is kinetic energy, and the solid line I'll say is potential energy. All right, so we'll do it that way. Okay, so now starting off, like again, I said the skater said it's maximum speed. Well, again, the maximum speed occurs right here. Well, looky here, the kinetic energy is the maximum. The entire energy of the system is kinetic. I would say that I would label right there on that graph. So again, the graph is the kinetic energy is at a peak right at the same location as the skaters at its maximum speed. So again, that would be the, and you notice the kinetic energy curve is right at the total energy at that point. B, the skater is stopped. Well, the skater stopped right where the potential energy is a maximum. So again, that would be like, I can call it like, let's say here, or you can look at it from the perspective of the kinetic energy if you like, and at the very end as well. And looking at it from the perspective of the either potential energy or the kinetic energy, however you like. In both cases, the potential energy is all there is. It's maxed out at the same line as at the same level as the total energy, and the kinetic energy is 0 in these cases. Let's see. C, the skater is going his average speed. Well, again, as I look at it, what did I call the average speed? When I say the average speed is right around C here, so it's right around where they kind of cross, I would say. So I would say maybe around here. Average speed. D, the skater is going slow. Again, slow occurs right where the potential energy is pretty close to a maximum, or the kinetic energy is near 0. So I'd put little D's, maybe, to indicate that. Again, depending upon the perspective of either the potential energy or the kinetic energy, whatever curve you're focusing on. And let's see, finally, the skater's going fast. Well, again, I would say fast would be right around where the kinetic energy is high. So here the kinetic energy, you can definitely see it's really close to the total energy. Again, I hope you can see this. I put little E's right around here. And I would say, I didn't draw this all that well, but I would say, fast is a qualitative term. So maybe here. And wherever the dash kinetic energy line is high. I think that's about it. And we have A through E. Is that clear?
Yes.
All right, so we're almost done. Now, number 8, we have 8 and 9 here. So 8 now says, I want to add an amount of track friction to the original skate track configuration. What's the kinetic, potential, and thermal total mechanical energy after 2 seconds? Explain the transfer of mechanical energy throughout the simulation when the skater finally comes to rest. Label each energy source as conservative or non-conservative. Explain each case. All right, so I'm done with this picture here. So I'm going to erase the board. And let's go back to the software. All right, so the software, what we're going to do now is we're going to do things a little bit differently. And that is, we're going to go back to what we saw before. We're not going to be in the double well. We're going to go back to the original. So I'll share my screen. All right, so before I said that there is no friction in the system. What I do basically is I'm going to go back to track friction. And I'm going to put the friction right around the middle. Right between the max and the min or so. Again, you'll have a different value than me. But I'm going to now put friction in the system. And now let's go back to what we were doing before. I'll return the skater to where he was before. And now what are we going to do? Well, again, we're on the Earth, and I want to know what the kinetic, potential, and thermal energy and total mechanical energy after 2 seconds. All right, and so I'm going to go back to my plot, energy versus time. I'm going to clear it. Okay, now we're going to have right now we're in initial configuration. We have that total energy of 2632.02 that we're familiar with. Kinetic energy is 0, all potential energy. But now we have friction. Now we're going to have frictional dissipation. So what happens now? Let's try to see if we can. I'm going. Let's have it set that simulation time too fast. I'm going to slow it down. All right, let's try to go to 2 seconds and let's kind of observe what happens now. So I'm going to go to 2 seconds and try to stop it, and we'll write down, or well, you'll write down what you see. Go a little further. Okay. That's pretty close. All right. So what you'll see here is that the thermal energy is increasing. And you'll notice that the kinetic energy and the potential energy, if I add the two up, so let's add the two up and see what we get. Do they add up to 32.02? Let's see, 75.91 plus 1348.48. Now they add up to 1424.39. Well, that's a value that is less than 2632.02. What happened? Well, there was a non-conservative work. There's friction. Energy was dissipated out of the system, a lot of it. Where did it go? Well, if you add that thermal term, so again, how are we going to answer this question? You would say what? I mean, well, 8A says, what is the kinetic, potential, thermal, and total mechanical energy after 2 seconds? All right, so this is a little bit tricky. The kinetic energy is clearly, you read it off the display as 76.31, for instance, joules. Potential energy, 1348.48, I guess that is, joules. Thermal, you'd read that as 1406.63 joules. Total mechanical energy really, well, I guess well, let's see. If you, yeah, this is a little bit misleading. The display says total energy, which is true, adding all the energy up. Total mechanical energy is kinetic plus potential. All right, so when you add the total mechanical energy, you would get kinetic energy of 76.91 joules plus potential energy of 1348.48 joules. You would get 1424.39. You would not want to write 2632.02. That's not total mechanical energy. That's total energy. Okay, mechanical energy is kinetic plus potential. All right. So again, let me stop sharing for a minute. I want to make sure I'm going to drive this point home. Mechanical energy is very special. Okay. Mechanical energy. So total mechanical energy, not total energy. That energy, I'll put a little M for mechanical, if you will. That's kinetic energy plus potential energy. All right, that's not thermal. Thermal energy is being lost in the system. All right, so that's how I would answer 8A. Kinetic energy, I can read it off the graph, off the plot. Potential energy, again, read it off the plot. Thermal energy, read it off the plot. Total mechanical energy at 2 seconds, it's kinetic plus potential. Don't just give me the total energy. Don't give me the total energy to read off the plot. That's the total energy. That's energy from all sources. But the mechanical energy is just kinetic plus potential. All right. B, explain the transfer of mechanical energy throughout the simulation when the skater finally comes to rest. All right, and so let's find out how long is it going to take for the skater to actually come to rest. All right, so let's kind of see how long the system goes until it dies out. So let's go back to sharing the screen. Okay, we stopped him at 2 seconds, but let's kind of watch it. And the system is just going to lose energy. So let's continue. Let's watch it. So we're at about, and notice the skater, he's going down to the trough, and he comes up not quite so high. comes down again. So, like, and again, the simulation is at the lowest simulation time. It's at, I slowed it down. Notice the thermal energy is going higher and higher. The thermal energy is actually approaching the total energy. This system is getting, essentially the energy is getting sucked out of the system. Okay, we're at 7 seconds. Things flattening out, it's flatlining. Again, he's still moving though. 8 seconds, still kind of going a little bit. And I usually see that he dies out at about 9 seconds. Now he's stopped. All the energy is now, it's been thermal energy. It's entirely dissipated. There's no mechanical energy left. All right. And so I answered this question kind of in the following way. I said, number 8, I said, I set the coefficient of friction slider to the bar to the middle. After 2 seconds, I wrote down my kinetic energy, my potential energy. I added the 2 up. For the total mechanical energy, I wrote down the thermal energy, just like I told you to do. For part B, I said the frictional work, which manifests itself as thermal energy, continues to extract total energy from the system till the system stops moving at about 9 seconds, T equals 9 seconds. And the skater ends up at the bottom of the track. No more energy left. He's pretty much, he's on empty. All right, so bottom of the track. Now, part C asks you the following. I want you to help me out here. Part C is asking 8C, says label each energy source as conservative or non-conservative, explain each case. So what are the forces? Again, we turned on friction. What are the forces in this problem? Can you name the forces? What forces are involved in this problem now, though, when I turn on the friction? We have gravity, right? Gravity, gravitational force. And the other force that we now have in the latter part of this experiment is friction. So, gravitational force, conservative or non-conservative? You with me?
Yeah, sorry, conservative.
Absolutely right. That was conservative. And again, we talked about that, and because it has potential energy, the work only depends on the endpoints. It is path independent. All that. You can talk about all that because I want you to kind of explain what why you say it's conservative. And then, what about friction? Conservative or non-conservative?
Non-conservative.
Non-conservative, because friction either adds or deletes. In this case, friction deletes energy from the system. Energy is lost. Non-conservative. Again, you can give a little explanation as to why. So again, conservative, why? Because we know that the work only depends, is path independent, only depends on the endpoint. The gravitational force has a corresponding potential energy. It's conservative because of these reasons. Friction, on the other hand, does not have a potential energy. And in fact, friction dissipates energy from the system. Conservative forces will never add or subtract energy from the system. Non-conservative forces will add or subtract energy from the system. All right, in this case, friction subtracts it. All right, number 9. And any questions so far?
I'm good so far, thank you.
We're at the end of the lab. So 9's pretty cool, I think. So what we're going to do now is just kind of just go back to the lab here, and what we're going to do is we're going to analyze Newton's laws real quick. So place a skater and track in space. How can this scenario validate Newton's laws of motion? So now we're going to go to space, outer space. All right, so let's go back to the lab. We're going to leave the Earth. And I'm going to clear energy here. What we're going to do is we're going to let me reset the I'll reset the skater. So we're really close here to the end. Return the skater. We'll slow down the sim time. What I'm going to do is I'm going to select not the Earth, not the Moon, not Jupiter, but I'm going to select space. And in fact, I'm going to completely take them off the track. Now, there is no gravity anymore. There's no reason for this skater to even move. It's completely weightless. There's nothing pulling it. No Earth, no Moon, no Jupiter. Now, the question is, well, you see the skater is at rest. Newton's first law says an object at rest will remain at rest unless acted on by a force. Newton's first law also says an object in motion at constant velocity will remain in motion at constant velocity unless acted on by a force. And again, constant velocity could be v equals 0. So yeah, nothing is changing this skater. Nothing is making this skater move. Now, what we can do at this point is we can apply thrust. Now, what I'm going to do is I'm going to show the energy time graph yet again, and I'm going to put it, kind of place it over the track because we don't really care about the track anymore. And you notice that essentially, well, we have the old values which don't really matter, but essentially what we're going to see now is if I can clear this and get better numbers, see if the numbers actually become okay. Well, they don't do much for me at all, but anyway, there's no gravity. We're in space now. What I'm going to do is I'm going to apply a thrust. So the arrow key, if I strike the arrow key to the right, the right arrow, I'm actually going to apply a thrust. So I'm going to apply a thrust briefly. Second, try that again. Trying to. Hang on. At least the arrow key. Okay, so this is supposed to work. So what's going on here? All right, now let's see. All right. Right arrow. Not working. All right, let's. All right, so it's supposed to. All right, let's go back to Earth and go back to space. I think Zoom is affecting things here. All right, the arrow key is supposed to. Num lock or something. All right, well, this is not working. Oh, you know what? I'm a goofball. I need to hit the play button. All right. Never mind. That was embarrassing. All right, let's do this again. All right, so I'm in space. I apologize. I'm a goof. Energy time graph. Okay, I actually have to hit the play button. So if you look, if you strike the play button, you notice that there's nothing. There is no kinetic energy, no potential energy, no thermal energy, no total energy. Now I'm going to strike the right arrow and I'm going to hold it down just a little bit. And I'm going to accelerate him, and I've accelerated the with the thrust. And notice now that there is a new constant kinetic energy. And it is constant, right? So what I've just shown you is that an object at rest tends to stay at rest unless acted on by a force. I accelerated it via a force. I applied a thrust, and then I let go of the arrow key. And then once I let go of the arrow key, I no longer have a force. So now it's going at a constant velocity, and it's going to go on forever at the constant velocity. An object at a constant velocity will remain at that constant velocity. Notice that the velocity of the kinetic energy is staying constant. That green line is the kinetic energy. It is at a constant value, and there's nothing that's going to change it because there's no force. Now, if I decide to, I'm going to hit the right arrow again. There you go again. Now I stopped. I lifted my finger off the right arrow, and now I'm going to coast at a new constant velocity, a new, again, a new constant kinetic energy. So again, what we're seeing here is Newton's first law of motion. An object, and again, I'll kind of write it on the board here. So we're asking the question. Let me reread the question here. Place the skater. Okay, how does the scenario validate Newton's laws of motion? So how is it? Well, again, Newton's first law. What is Newton's first law again? An object at rest will remain at rest unless acted on by a force. Okay. Well, in outer space, there is no force. So the object, the person is just going to sit there in outer space. Now the person turns on the thruster for a moment and then turns the thruster off. And the person is going to end up, saying, okay, well, I'm starting off, V equals V naught plus AT. All right, now my V naught, I'm sitting still, V naught is 0. So I'm going to accelerate for some amount of time t, and I'm going to attain a new velocity. And then Newton's first law, the rest of it says, an object in motion at a constant velocity will remain in motion at that constant velocity unless acted on by a force. So once I turn off the thruster, it's just going to coast at V, constant velocity forever. All right. So that is how you can use this software to validate Newton's first law. And of course, Newton's second law, there, as I wrote that equation down, there's an acceleration. So Newton's second law, you could also validate and say, well, I applied a thrust force. So again, what's Newton's second law say? Well, the second law says the following: sum of all forces is mass times acceleration. Well, I'm going to do it in one dimension. So the only force I have is, say, the thrust force. The body, 75 kilogram mass, is going to accelerate. So that acceleration, when I saw, again, you can measure this more accurately. When I saw that V equals AT, given that V naught was 0, well, that acceleration, I could actually calculate and say, well, what is that? That's the thrust divided by m. Again, T is what? T is the thrust. So some sort of a thrust force. And so that velocity, I can plug that in here. And that velocity is just going to be the thrust force divided by the mass, because that's the acceleration, multiplied by how long you turn the thrust force on. So again, you can see the action of Newton's second law as well. And you can see this very nicely in outer space because there's no other forces to impede your experiment. Okay, so you're in outer space, there are no other forces. And that is really that's the lab. So any questions? I don't have anything else.
No, I'm good. Thank you.
Yeah, so the main part of this write-up is going to be, labeling those pictures that I talked about. And so how I labeled those pictures, I went over all that. We had a couple of pictures of the tracks that I drew. One was the regular track, one was the one that had the double well, and then there's the potential energy where I label that. I mean, that's part of what you want to turn in. And then the other thing you want to turn in is you want to turn in additional pages where you show those calculations for 1 through 4. You show those calculations for Earth, Moon, and Jupiter, and again, you answer the questions. And then again, on the second page, we just got done talking about number 8 and number 9. So anything that's a question, you're going to want to turn in, redraw those pictures, labeling them. Again, those calculations for the Earth, Moon, and Jupiter, and then finally those last couple of questions we just got done talking about. So again, I did most of that for you. But what I like, you and all the other people watching this video, I want you to fire up this experiment yourself and do this. And I'm guiding you through it. And of course, you're going to have to do it for the Moon and Jupiter because I didn't do those. But again, it's the same steps. All right. So you all good?
Yes, sir. Thank you.
All right. Thank you.
Have a good night.
You too.